that we have been working on in the past 3-4 years. We were interested, we ended up working in topological models because we started working on geometry of Banach spaces. Then we jumped to topological vector spaces because we wanted to find out if there's some type of geometry involved there in the linear and topological structure of topological models, which is the you can define some type of certain subsets which provide geometry to those spaces, and then from there the natural step is to jump to topological models. So these are the contents of this talk. I'm going to talk about a little bit of model geometry, fine model topologies, derivations, limit operators. Then I will get into representations of groups, mostly linear representations, topological representations, and then finally I will talk about a famous problem on representation theory, which is the complementation of this submodel, or typically subspace, or in this scope submodel of invariant vectors. So I'm going to talk. So I will start first with the first section, model geometry. Well, first of all, some conventions. All monoid actions considered will be left. All rings and algebras will be associative and unitary. All models, rings, absolute semi-values, semi-norms will be non-zero. We'll consider non-zero. So all trivial cases we will just disregard. All models over rings will be unital, meaning that 1 times m is equal to m, and unital semi-norm ring or algebra means that the norm of the unity is just 1. Well, we started defining unit zero neighborhoods because in order to transport the geometry of topological vector spaces, which relies so much on the underlying field, which is the real or complex field, we need to extend the concept of unit ball to rings and models. So then we came up with unit zero neighborhood. So in a topological ring, we have two subsets. So U is called an open unit neighborhood of zero, provided that U is additively symmetric, multiplicatively idempotent, and a regular open neighborhood of zero, so that one is in the closure of U. Let me remind you that regular open means in a topological space, regular open means an open set which coincides with the interior of its closure. And B is called a closed unit neighborhood of zero, provided that B is a regular closed and its interior is an open unit neighborhood of zero. Then we had to classify this type of neighborhoods of zero. Well, first these two trivial observations. If U is an open neighborhood of zero, then the closure of U is a closed unit neighborhood of zero, and if B, conversely, if B is a closed unit neighborhood of zero, then interior B is an open unit neighborhood of zero. But this is just by definition. The only proper closed unit neighborhood of zero in the reals is just the interval -1, 1, and in the complex case it's a little bit different. The only proper closed unit neighborhood of zero in C, containing the unit complex numbers T, is the closed unit disk. And more generally, if A is a unital real Banach algebra, then the unit ball is an open unit zero neighborhood, and the closed unit ball is a closed unit zero neighborhood, which makes these definitions consistent. So now we also had to extend the concept of segment in order to have some type of convexity. So then we also have to extend the concept of segment in order to have some type of convexity. So then we also have to extend the with its opposite is zero, and 1 plus its opposite coincides with that set where B to B negative is just negative B plus. Okay, it's called negative unit segment. This is how you define B negative. Well, it's easy to see that in a topological ring there exists a unit segment if and only if the characteristic of the ring is different from 2. In this situation, it can be found a maximal unit segment. And well, some examples. This proposition or this sentence allows to construct many. Well, with these two, allows to construct many unit segments whenever a topological ring the characteristic is different from 2. So if you have a torsion-free algebra over an integral domain, then B plus, and if you have a unit segment in the underlying ring, then automatically you obtain a unit segment on the algebra. Okay, and this is an interesting theorem that we observed, which connects this theory with the theory of effect algebras, which are important objects in quantum mechanics. If R is a topological ring and you have a unit segment, then if you consider this subset of the direct product, okay, or elements that so that its summation is in B plus, then the addition restricted to this subset, so which makes the addition a partially defined binary operation. With this structure and with this complementation, this becomes an effect algebra. Okay. Well, then now we can start having some geometry on topological models. If we have a topological model or a topological ring, and we have a closed unit neighborhood of 0 and a unit segment, then a subset is B balanced, provided that B times A is equal to B. B absorbing, provided that for all M in M there exists an invariable, so that the B times M is contained in U times A. So U absorbs M and is B max convex if for every finite elements in A, the geometric simplex, okay, which are these linear combinations with summation equal to 1 in the B mass set, is contained in A. Okay, and finally is B plus absolutely convex if A is B balanced and P mass convex. Okay, so this concept generalize the classical concept of balancedness, absorbance, convexity. Okay, so now we can define locally convex model topologies. A topological model or a topological ring, if we consider a closed unit neighborhood of 0 and a unique segment, we say that the model topology is locally B mass convex if there exists a basis of B mass absolutely convex and B absorbing neighborhoods of 0. So we will prove now, well, we managed to prove that if you consider suitable closed unit neighborhoods of 0 and suitable unique segments, which can be found in many topological rings, then there exists the finest locally convex model topology, which is the following theorem. Well, like I said before, we need first the suitable closed unit neighborhoods of 0. In this case, a closed unit neighborhood of 0 is called left feasible, provided that U times B, where U is an invariable, is a basis of neighborhoods of 0. Okay. In a similar way, right feasibility can be defined, and B is called feasible if it is left and right feasible. Okay. And the suitable unit segments that we are going to need are they are called feasible, and they verify that 1 plus 1 is invariable in the ring, and the inverse belongs to the unit segments, and also the unit segment commutes a set. Okay, it's not a local commutativity, just a sec product with every element in the ring. In particular, for commutative rings, this is automatically satisfied. So now, if we have a module over an integral domain topological ring, we need the integral domain condition. We have a feasible closed unit neighborhood of 0 and a feasible unit segment, then the collection of all B plus absolutely convex and B absorbing subsets of M is a basis of neighborhoods of 0 for a module topology in tau n, which is going to be trivially locally convex, and in such a way that even more, if tau is a locally convex module topology, then it is contained in in this one. So this is the finest locally convex module topology. Well, then we also work on derivations, because we were interested in extending the concept of differentiability to this scope. So, well, let me remind you what a derivation is. If you have a bimodule over a ring, a derivation is simply an additive map, a homomorphism of additive groups that satisfies the product rule, okay, that we all know. There are many examples of derivations. They are studied. They have been studied a lot in operator theory. Mostly the inner derivations are very famous in algebras. Okay. Well, so in order to define, we're going to construct a particular derivation in this setting, in the setting of topological models. But we need to consider not any topological ring is valid. We need to consider topological rings for which 0 is in the closure of the invertibles, because otherwise you can't take the limit as at 0. Okay, so a topological ring is called practical if 0 is in the closure of the invertibles. Well, any topological algebra over a non-discrete division ring is practical. This is trivial. And if R is a practical topological ring, then 0 is not an isolated point of the invertibles union 0. So the collection of all reduced neighborhoods of 0 in this notation means if X is a topological space, sorry, if X is a topological space, n sub 0 of X, well, sorry, if X belongs to X, then n sub X of X, this is the collection of all, well, this is the collection of all neighborhoods of X. And if we write as subscript times here, then it means the collection of all reduced neighborhoods. Okay, this is just a standard notation from topology. So, well, so actually that collection is a filter. Okay. So, for the reduced, for the collection of reduced neighborhoods, then we need 0 not to be isolated. We need this point, that point in particular, not to be isolated in order for this to become a filter, in particular a filter base, and then we can take the limit. So, well, with this, now we can define the classical definition of rate of change, okay, which in this setting is, remember that We are considering left modules, okay, over rings, because all actions are considered by default left actions. And then we have the rate of change of a function defined on an open set with values in another mode, okay? And then if the limit of this function at 0, since the ring is practical, 0 is not isolated, I mean, can be approached by invariables. And so then we can so this becomes a filter base. So then we can take the limit as r approaches 0, and that limit is defined as the directional derivative. Okay, keep in mind that here we are not considering, we're not assuming that neither m nor n is Hausdorff. So then this could be, well, the limit is a set. Okay, only when n is Hausdorff, this could be either empty or a single. Okay, but, so this is how we define the derivative. And then finally, well, we now define the differential. Okay, this is essentially the same construction with as the Gato derivative in a Banach space. Okay, sorry, here. So then we have a map from an open subset of a topological model into another topological model. We say that f is differentiable, provided that f is differentiable at every n. Okay, and this is the differential of f. And this differential is going to become a derivation. Okay, we define the set of continuous and differentiable functions. And finally, if we give a structure of algebra, because in order to have a derivation, we need a ring and a bimodule over the ring in order to have the product rule. So if we have if now we assume that n is a Hausdorff topological algebra, then this map is a derivation. Then we continued working with limit operators, because we wanted to extend some results or some classical results that we worked on in the past on Banach spaces, which are the famous Banach limits, to the scope of topological models. And from there, by relying on the concept of Banach limits, then we came up with this concept of limits operators, which can actually be defined not only on topological models, but on topological spaces in general. So, but first I have to recall several classical definitions. For example, Hull operators, which are simply set value operators, okay, for just functions from power set of a given set into the same power set, verifying the following conditions. Extensivity is contained in H of A, increasingness, A contained in V implies H of A contained in H of V, and idempotency. Okay, H squared is equal to H. And the classical example of Hull operators are the convex Hull or the linear span. Even the closure in a topological space is a Hull operator, is a special Hull operator, because in general Hull operators do not necessarily map the empty set to the empty set. Actually, the linear span doesn't map the empty set to the empty set. The linear span maps the empty set to 0. Okay. A closure operator, which I mentioned before, that this is also a classical definition in topology. It's just it's a special type of Hull operator. It verifies the nullity. This one maps the empty set to the empty set. extensionality, additivity, and idempotency. Okay, so with these properties, you can prove that a closure operator is a good operator. Well, yeah, here actually it is mentioned every closure. Well, no, this is a different thing. Every closure operator on a given set determines a unique topology. This is also a classical resulting topology, whose closed set are precisely described by the image of C. Okay, so these are classical thing. So now, by relying on Banach limits, we can construct limit operators which induce closure operators, and the topology induced by those closure operators, induced by the limit operators, are almost compatible with the limit operators. So in a set, for every x, we will denote, I don't know, this x, blackboard x, denote the constant sequence of general term equal to x. Okay, and we also define the following preorder. Okay, this is not an order relation; it's a preorder because it doesn't satisfy the anti-symmetric property. On x to the so on the set of all sequences on x, a sequence is less than or equal to another sequence if only if A is a subsequence of B. Limit operator, this is a definition from us, is a map from the set of all sequences to the power set, satisfying the following property. X is obviously belongs to a limit of the constant sequence of general term equal to x. If A and B are sequences and A is less than or equal to B, so I mean if A is a subsequence of B, then the limit of B is contained in the limit of A. And if B is a sequence, X is in the limit of B, and every element of the sequence is also the limit of another sequence, then you can find two subsequences of numbers, so that X is in the limit of C, where C is equal to where the sequence is defined this way. This here is a little bit how do you say, strange, but it really makes sense. This condition is just saying that if X can be approached by B, and every element of B, of the sequence B, can be approached by another sequence, then X can also be approached by a subsequence of AN. This is basically what he's saying. So now, if X is a set, then a limit operator, every limit operator defines clearly a closure operator, which is the union of all sequences of the limits of all sequences of A. Keep in mind that this could be empty. Okay, in a closure operator, in a limit operator, not all sequences must have a limit. You're going to have here the empty set. Actually, if you take any topological space and you can define a limit operator by considering the limit of the limit set of any sequence, and that operator verifies all these conditions. Trivial. So finally, if you have a limit operator, if you consider the closure operator induced by the limit, and if you endow X with this with the topology induced, with the unique topology induced by the closure operator, then the limit, then L of X is contained in the limit as n tends to infinity of Xn for every sequence for every sequence of X. Okay, where this is the usual limit in this topology. Well, now after we developed all these tools in topological models, we jumped into representation theory, because mostly because of this problem. because of the problem of complementation of the subspace of invariant vectors, because we have been working with projections for quite a long time, and we saw this problem as a very interesting problem, and so this is why we got involved into this. But the thing is that in order to work on this problem, you must have some notions of representation theory first, which is well, still have 15 minutes. So I'm going to talk about this now. Well, just classical definitions. A categorical representation of a group is simply a group homomorphism of a group into the group of automorphisms of an object. This should be A here. Okay, instead of C is the category. You have a category and A an object of C. A categorical representation of a group on the object A is simply a group homomorphism of G into the group of automorphisms of A. Okay, it's a category. A is an object. So a representation is a group homomorphism from G to the group of automorphisms of A. A particular case, by using the representation by left multiplication, a particular case of categorical representations are the algebraic representations. Okay, an algebraic representation of a group G on a ring R is simply a group homomorphism from G to the group of invariables of R. Okay, this you can embed this group isomorphically in the category of groups inside the group of automorphisms of the additive group of R by using left multiplication. So then this is this makes this representation a particular case of a categorical representation. Okay. Well, typical example is the symmetric group represented in the general linear group. It's a classical representation by permuting a basis, a fixed basis. Okay, just a classical example. Well, star rings. Well, we first recall that an involutive element in a multiplicative monoid is an element whose square equals the unity. And a star ring is a ring endowed with an involution, okay? That is an additive, anti-multiplicative, and involutive for the composition map, okay? And C-star algebras are clear examples of star rings. Well, this is just a simple remark which allows to define star representations, which are the basis of the dual representations, which are going to be very important in order to accomplish complementation of subspace of invariant vectors. So a star representation is simply a group representations on the group of invertibles of a star ring, and it is defined. Okay, you end up with, sorry, you start off with a representation of a group on a star ring, and then pi star is the star representation of pi, which is defined this way, which is the star element of pi of the inverse of G. Okay. Linear representations are the most used representations in operator theory, in analysis, okay? And are particular cases of algebraic representations, which are particular cases of categorical representations. So if a module, so we recall that Fm is a module over a ring, and L of M is a ring with a composition, and the general linear group of M is just the invariables of, I mean, the isomorphisms, the linear isomorphisms, which is also the group of automorphisms of M in the category of modules. And linear representation is simply a representation of G in the ring L of n. Okay, L of n is the ring of linear maps from on n. Okay, so this is the group so this is a linear representation. If we consider topological models, then we have topological representations. Actually, these topological representations are defined after linear representations as particular cases. Okay, because the topological general linear group is clearly a subgroup of the general linear group, but you can regard all linear representations as topological representations also, because if you have a model over a ring and you have no topological structure, you can always endow both of them with the discrete topology. If the ring is endowed with the discrete topology and the model is endowed with discrete topology, then those topologies become model topologies. Okay. And automatically the topological general linear group coincides with the general linear group, because all linear maps would be continuous. And finally, dual representations. Well, this is just basic observations from algebra. If M is an R model and N is an RS by model, then the linear maps is clearly a right S model, and that makes the dual a right R model. This is something that is important to take into account in this scope. If you have a left module, the dual is a right module, and the bidual is a left module. Okay, it's a switch. And a dual representation is just, well, the dual representation of a topological representation is defined the same way as the star representation of a representation of a group on a star ring. Okay, it's just defined the same way. So this is why star representations are considered, because of this. And then we have isometric representations, but in topological models, operators norms don't work the same way as in the real or complex case. Okay, so you need to ask the semi-norm ring for certain properties in order for the dual of an isometric representation to become an isometric representation. So, well, an isometric representations, as you can imagine, is simply a representation of a semi-norm of a group in a semi-norm module over a semi-norm ring in the group of surjective linear isometries, which is a subgroup of the topological general linear group, which is a subgroup of the general linear group. So now, in order for norms to work on modules, we need to consider special types of semi-norm rings, which are called normalizing, and those are rings that verify these conditions. A semi-norm ring is normalizing if every semi-norm module over R, M over R satisfies that for every M in M with norm of n still greater than 0. There exists a sequence of invariables with norm less than or equal to the inverse of the norm of M, but the inverse of the invariables, the norm approach M. Okay. Well, before going on, we must characterize this type of rings, because otherwise we need to know how many of them are there. They are not completely classified yet, but at least in the absolutely semi-valued case, they are characterized. They're not classified, but characterized. And the characterization is that an absolutely semi-valued ring is normalizing if and only if the range of the absolute value is over the variables is dense in 0 infinity. So in particular, every absolutely valued algebra over Q preserving the Euclidean absolute value is normalized. Okay, here it's important that the absolute value of the algebra preserves the Euclidean absolute value of the rational, because it doesn't work. You don't have this density if you endow the rational, for example, with a p-adic absolute value. Okay. Now we can make the following observations. If M is a seminorm left module of a normalizing seminorm ring, then the dual is a seminorm right arm module with a dual norm, and the bidual is a seminorm left module with a bidual norm. And now, as surjective isometry between seminorm modules of a normalizing seminorm ring, this is the key part. Its dual map, sorry, this is also a misprint. This should be n star to m star. Okay, it should be as we know, E star n star to m star. As we can start continuous surjective linear symmetry between m star and star when m star are endowed with the dual norm. Okay, and so finally, if pi is an isometric representation over on us in a seminorm module over a normalizing seminorm ring, then the pi star is also an isometric representation. And finally, we can finally work on invariant vectors. Well, first let's recall some classical concepts of invariance in actions, because this the theory of representations is extremely linked to the theory of actions. Okay, and the concept of invariance is historically comes from the theory of actions. Okay, so we have an action of a monoid on a set S. A subset T of S is G invariant, provided that G of times T is equal to G, and an element is G invariant if so is the unitary set consisting of that element. And every linear representation naturally induces an action. Okay, actually the other way around. An action of this form, an action of a group on a module also induces a linear representation. Okay. Here. Well, now since every linear representation induces an action, we can transport the invariance of actions to linear representation. And that results into the submodule of invariant vectors, which is defined this way. All elements which are invariant under the under pi of G. Keep in mind that pi of G is a continuous linear map from M to M. Okay, for all G. And M, that is M sub G, and M sub G is defined as the pre-annihilator of the submodule of invariant vectors in the dual representation. Okay. So now the main question is when M sub G is complemented along M sub G. That's the main question. Well, first we have one minute left. First we have a formula for the submodule of invariant vectors, okay, which is so in a topological representation now we need M to be a Hausdorff topological module over a Hausdorff topological ring. We haven't used it until now, and the invariant vectors of the dual representations coincide with the annihilator of M sub G. And finally, the complementation of, I have two slides, or two or three. If we have well, in order to we want to accomplish the complementation of M sub G along M sub G. So then what we did is we started with a necessary condition. I mean, we assumed that they were complemented, and we tried to find out what's going on. And then it happens that you have these contentions with the dual projection, which gave us a lot of hints in order to find sufficient conditions or to characterize when M sub G is complemented along M sub G. And these conditions turned out to be possible in the scope of isometric representations by using the concept of supporting vectors and supporting functionals. We can, if we consider supportive representations, which verify the following, that the supporting functionals of elements always intersect the invariant vectors of the dual representation, and the same for in the predual. And there are plenty of examples of supporting isometric representations in the real and complex case. Then we finally could prove the final theorem in an isometric representation of a group on a norm module of a normalizing absolutely valid ring. If pi is supportive and we start supportive, and M is strongly torsionless and complete, then M sub G is one complemented in M along M sub G. And here we obtain something similar for the complementation in the dual representation. Fine. And this is the end of it. Thank you very much. I'm sorry for
the whole theory. So if there are questions.
Can you hear me?
Yes.
So I'm curious about if you could suggest some historical comments here, when some of these concepts were introduced, and
In representation theory.
you started with intervals and things like that.
Intervals. Yeah. I know. I think you are. I don't know how to go to the fair. Well, you mean the at the very beginning, the closed unit neighborhoods of zero.
Yes.
Yeah, we defined that maybe 3 or 4 years ago, and also closed unit neighborhoods of zero and unit segments.
Mm-hmm.
And representation theory that mostly comes from differential geometry. Exactly the historical origin, I don't know, but one of the first mathematicians working on representation theory was, I don't know if I'm able to pronounce the name correctly, Kashdam. But they work on representation theory in the context of amenable groups, which I don't work with that. I do it more. I connect it more with topological models, in the sense that from the perspective of topological vector spaces. This is what they do is more geometry, is more differential geometry, and this is more functional analysis. But they are like Kashdam is one of the. Actually, he has a couple of books on representation theory, which are like the Bible on that.
Okay. I think you've answered my questions. Thank you.
Welcome.
I'm afraid that we have no time.
Sorry.
Questions, so thank you very much.
You're welcome. Yeah.